First of all, I'll just show you this video, very brief one. Very old video, it shows mixing. Yes, I'm talking to a microphone. I can speak like this. Up. Even up. Turbulent mixing is very fast. It's obviously reversible. When we mix two different liquids, it's quite difficult to unmix them. And lamina is a little bit slower, but it's still a reversible process. It's still reversible. So it's easy to mix, but very difficult to unmix. That's because some of physical laws, like second law of thermodynamics, are time directional. If thermodynamic time stops, we won't be able to mix two different liquids. And the question I'm going to ask today is a little bit strange. So slideshow is here. Is about would mixing be any different in some very remote part of the universe? In other words, whether thermodynamic time would continue or it might just stop. It looks like a silly question, and just to warn you, I'm not going to suggest any answer. I'm going to ask only some questions, and if the audience have some answers for these questions, you're most welcome to tell us. So I will try to leave. I would like to follow directions from the chair and from the director of this institution and leave some time for discussion. And the first speaker actually touched this question. When we're trying to reverse time, whether we're going back to original initial conditions or we're not. Do we have reversible or irreversible processes? In real life, of course, we have both. Okay, let's just mixing. What is mixing? There are different types of mixing, but mixing is a signpost of time because it's a irreversible process. And we have mixing of two gases. We have mixing of energies. When energy goes from higher temperature to lower temperature, again, it's an irreversible process which increases entropy. And everyone knows this. And the third mixing I would like to mention is a mixing at quantum level. When you have pure states and then somehow, due to some processes that we don't know exactly, these states can be converted into a mixed state. So again, this process increases entropy. Unitary evolutions of quantum they preserve entropy, but this is an analog, quantum analog of mechanical mixing. Okay. Now, yes.
A very brief question. You mentioned energy mixing and like material mixing, mixing of matter.
Yeah.
But traditional hypothesis, I just would like to follow, what you say. Traditional hypothesis is that both of these processes, they are associated with multiple collisions of particles, right?
Yeah, of course.
But it may be something else. In principle.
Yeah, it might be.
Because energy may go not only through the multiple collisions of particles, multiple inelastic collisions of particles, but it may be transported by a number of other means, through different degrees of freedom, not necessarily translational.
Yeah, that's a question we're going to discuss right now. Yes, but so on one hand, all these mechanical collisions, they seem to be perfectly reversible. As we speak about the whole process, obviously entropy increases and it's a reversible process. We all know this, and it's a big issue which has been discussed since Boltzmann times. So, and I would like to give a slightly different view on this. Yeah, that's exactly the process we're going to discuss. First, and what we have here, we have the basic fundamental laws of physics that we know that are reversible. Mechanics, relativistics, general theory of relativity. What else? Quantum mechanics, unitary evolutions are reversible. Yet what we observe in the real world is highly time irreversible. It's time directional. We remember the past, but we don't remember the future somehow. So what's the explanation? And one of the possible explanations, and many people share it, I'm not saying it's wrong, just is that we have very low entropy beginning of the universe, some low entropy conditions in the universe in the past, and relatively high entropy conditions somewhere in the future, and this on itself might be an explanation of irreversibility that we observe. So we assume all physical laws are exactly time symmetric, yet we have this inequivalence of initial and final conditions, which creates this inequivalence of the world that we observe. That's past hypothesis. Many physicists would say, yeah, that's an explanation. Okay, let's discuss it a little bit further. Of course, conditions imposed at universe, low entropy beginning is very important. But is it sufficient to explain what we observe? And first we're going back to the mixing and this initial example, when initially we placed all particles in one box, then we removed the membrane and particles started to distribute. Molecules, for example, they start to distribute evenly between A and B. Every molecule moves reversibly, yet we go from these conditions to that conditions. And this discrimination of time is determined that we set initial conditions and not final conditions. And we can set initial conditions, low entropy initial conditions, because entropy increases in this process. We can set it because we have low entropy conditions in the universe. So we can use some exergy to physically create these conditions here. And then we can proceed, and obviously this inequivalence of initial and final conditions creates increase of entropy and direction of thermodynamic time. Yeah? Next example. A little bit more complicated. So, we consider a gas. It's a thought experiment, so we are concerned with the gas, not with the cylinder, not with something else. And what is happening? This gas stays, yeah. Okay, sure.
When you say the initial conditions on A and B, like, here, what is the prescription? It's like, their velocities are prescribed, their distribution is prescribed.
What we force? We force that every particle stays in A at the beginning, and not
Do they move?
Oh yeah, they're molecules, so they keep
move
moving.
Randomly?
They move randomly.
So
they
they
have
based on distribution, like Maxwellian distribution, or?
Yeah, we can assume they have like thermal distribution, so they're in equilibrium but they're all located on one side.
So you quantify by location of certain particles with a certain distribution. So for instance,
yeah, they are. We always assume thermodynamic equilibrium.
Yes.
If nothing else is specified, so they have Gaussian distribution of their velocities. And they're molecules, in fact, because if they're particles, the entropy increase will be just small. And they're molecules, and they will start from this picture here and proceed to that picture over there. Like I couldn't draw many molecules. That's how my skills allow me. So just very few particles are shown there. Yeah. All right. Gas is our focus. What is happening? We stay in complete equilibrium for billions of years. For 1 billion of years. Nothing develops, complete equilibrium established, and then the whole influence of the whole of universe on this gas is that piston is moved at some stage in a perfectly time symmetric manner. It moves up, stays there, and then moves down. Initially, it's a slow process, so it's a diabatic slow process. Entropy is preserved, so everything seems to be reversible. Influence of the universe is perfectly time symmetric. After this process is completed, we have again 1 billion years of equilibrium. Yeah? So we screen our experiment from initial conditions imposed on universe by billion years of equilibrium, and from final conditions by billion years of equilibrium. We have only one influence applied to this gas, external influence, which is time-symmetric motions of the piston, and gas responds in a time-symmetric manner because laws of physics, as we assume, are time-symmetric. Logical? Okay, let's try to do something else. We run many of these experiments in many different parts of the universe in order to remove any influence of like environment. We move it away from any planets, very far from here. So, and again, what we'll do then, we'll move piston, we'll move faster, faster, and faster. And at some stage, if this experiment is conducted on Earth, here, there would be some asymmetry which would appear. When we move piston in, it's a shock wave. And when we move piston out, it's a rarefication wave. And they're not similar, as you know. They're not similar. They're different. They're different. And that's because entropy would increase in these processes if we move piston sufficiently fast at some speed. Yeah? That's what we observe on the Earth. Or here, for example, if we move piston sufficiently fast, remove it, we actually come back to original problem. When gas is concentrated, I cannot show you. When gas is concentrated here in this part, in the top part of the cylinder, and this part is empty, and then it propagates from A to B, as we considered previously. All right, now think again about this. This experiment is screened from initial conditions and final conditions imposed on the universe. There is no influence, no direct influence. I must be clear, no direct influence that we understand, no stochastic influence. The only influence of the universe on this thought experiment is time symmetric. No influence from some external environments, external bodies, galaxies, whatever you like to imagine. Yet, the response of this system is not time symmetric. You see? So this path hypothesis, either it predicts, okay, we take this experiment, we move it away, and it tells mixing will stop. There won't be any thermodynamic time running forward. That's one possibility. And another possibility, of course, is that there is some hidden mechanism which we don't know. We cannot specify it explicitly, but there is a mechanism by which some initial conditions imposed on the universe and final conditions somehow penetrate into this experiment. I call it time primer. So it's either time primer mechanism, which we don't know, a placeholder for mechanisms that we need to study, find, determine, and show experimentally that it indeed works, or we try to mix our tea with milk in a remote part of the universe, and it doesn't work because thermodynamic time stops there. It's either or. Now, maybe can I conduct experiment? Who thinks that thermodynamic time would stop if we move this experiment into a remote part of the universe?
How do you define thermodynamic time?
You can mix. It goes forward, entropy increases. Just you run. If it stops, it means that you have physical laws are satisfied, but entropy stays the same. You try to mix tea, and it would be more like, you know, when you have superfluidity. You cannot mix two superfluids because the flows are potential.
So there should be some time scales.
Oh, there is always a time scale, of course. But as you start to move away, and you screen your experiment from initial final conditions, and you screen your experiment from influence of other big galaxies in the universe, thermodynamic time might stop. Yeah.
I would like to understand whether when we talk about mixed transitional processes, or you're talking about fluid dynamical processes, because as far as I'm concerned, turbulence stirs, diffusion processes mix. They occur at different scales, right? So when you showed, for example, your teacup there, in my opinion, at the beginning you had stirring, and then only after that you got mixed, right?
Yeah.
Not necessarily.
Okay. So even fluid mechanics of pure fluid, it has some irreversibility which is determined by viscosity. Viscosity might be small, but it's still present. It's enhanced by turbulence.
So the way I look at it, so of course all the transport processes are responsible for the dissipation, right?
Yeah, of course, yeah, dissipation, which is a irreversible process.
Yeah, it's irreversible. So when we have the enthalpy equation, we have the reversible part and the irreversible part. The irreversible part is the dissipation, right? Okay, transport processes do that. That's entirely my point, is that when you start stirring, when you start your motion, it's basically a stirring motion. It's only after a while that you get your transport processes. These molecular transport processes are at a time scale that is much larger, usually, than the time scale of the flow, right? And so only after a while do you get these dissipation processes. And in my opinion, the way my terminology is, the mixing takes place, right? And what I'm going to show, and it's something that's sort of well known, it's not something that we were the first to show, that there are two types of diffusion. One is a regular diffusion, and the other one is called uphill diffusion. Uphill diffusion was sort of discovered only very recently, 1962. Okay? But it's so well known that it's used in industrial processes. So there are review articles, etc. An uphill diffusion, you can start with a uniform system and develop a non-uniform system. And still, you have.
And does it increase entropy? Okay, we need to proceed with the talk. Shorter questions are all right, but a longer speech you better wait to the end or maybe speak during your presentation. Just one question about what you suggested. This uphill diffusion, does it increase entropy?
Yes, it does.
Okay, so it doesn't matter. So anything which increases entropy is fine with them. Yeah. Okay, so how much time I have?
Well, I've been assuming that the discussion is
Okay, sure.
spread in the talk.
I'll just make my point, and then I'll speak a little bit about quantum version of mixing. Okay, so that would take probably like 3-4 minutes more. Okay, so that's the question I wanted to ask. If you believe that thermodynamic time will stop or it won't. If it stops, it means that entropy cannot increase or only reversible processes can occur. If you believe, and probably most of you believe that it won't stop, and I kind of more inclined to believe in it. I don't have any evidence, I'm not claiming this, but then there is no explanation. If all physical laws of quantum mechanics, laws of relativity, laws of mechanics are time reversible, and we screen our process from all influence of universe, why irreversibility, why time asymmetry appears? We don't have explanation for this, and it must be. If we believe in nature that has some physical laws that control it, there must be physical and testable explanation. That's my first point. Or indeed, if you move very away, time, irreversible time, thermodynamic time, which increases your entropy in different forms for different types of mixing, it can stop. Now, another point I wanted to make, Hans Reichenbach suggested that indeed thermodynamic time won't stop in the remote part, that it behaves more consistently and increase entropy, and there is no explanation for this. That's two possibilities that I just discussed. Now, we cannot possibly run this experiment and going to some remote part of the universe. Hypothetically, yes, we can think about this. Practically not. Can we run similar experiments? Maybe. Because if we speak now about quantum mixing, there are two different theories of quantum mixing. One is environmental and another one is intrinsic. And the first one aligns with essentially environmental decoherence aligns well with the past hypothesis. Laws of physics or laws of quantum mechanics are time reversible, but we have some influence of environment which creates this irreversibility. And the second one, we just have this irreversibility built in at some very small scale. I don't know which one is right. I'm saying there is an alignment, and might be possible to run some quantum mechanical experiments. But the problem is that theories of decoherence, they produce very similar predictions. So if you use environmental decoherence, and that's intrinsic, that's the prediction, and environmental decoherence is basically Zurich's theory. An explanation is you have some quantum mechanical eigenstates, and you have some coherence between different waves. As you have environmental influence, they change phase slightly, and this phase is essentially randomly because there are many different influences, and this coherence is lost. Once you trace out external degrees of freedom, what's left is essentially a decoherent state. So it's very similar to intrinsic decoherence. But it seems, I don't know, it seems I found a case which is quantum tunneling. And quantum tunneling has a very interesting feature. If you put particle or wave in A initially, and then you run and see if you find anything in box B, you do find in box B if you have resonance case. So basically these boxes are the same, or in any other form of resonance. It goes from A to B, then returns to A, then goes to B, and it's a periodic process. If it's non-resonance case, it would just appear slightly in B probability, but not much. So even a slight change in the size of box B compared to box A would result in a loss of resonance and completely different behavior. It seems like conventional theories of intrinsic and environmental decoherence, they give different predictions for this case, which is testable, which is physically testable. So it seems I found a case where conventional theory of environmental and intrinsic decoherence give testably different predictions for how a system is going to behave. And this might be a way of experimenting whether our hypothesis A or hypothesis B is correct. I'll stop at this point and maybe some other people.
Right, so actually we're into break time, so we should probably just move the discussion into the break.
Sure.
But thank you for a very... I'm sorry, what? Okay. So, well, thank you for a very interesting talk.
This isn't so much a question as a comment, everybody can't resist that, but I'd like to argue that entropy is somewhat of a subjective quantity, and it depends on measurement. You have to measure something, and if it's deterministic, you can measure everything, and then there's no increase in entropy. You decide not to measure something, then you say it's random, but if you measure everything, then it's not random. So you have to bring in quantum mechanics to make it random. So I think you have to be careful about how you define entropy. Different people would see different entropy depending on their
different
ability to
definitions.
measure.
Yeah, there are different definitions of entropy, and classical would be Boltzmann one, and Gibbs definitions. They're not exactly the same, and it's arguable. And quantum definition, again, it's it's a different definition, and it can be argued one way and another. But what we know, and we know for sure, that the world that we live in is time directional. You remember what you've done yesterday, but you certainly don't remember what is going to happen to you tomorrow. You see, whatever entropy, not entropy, some other effects, this world is time directional. And it would be very difficult to argue against this very important fact. And the question comes, why? All physical laws are time reversible, yet the world we live in is time directional.
I don't think it's a question per se, it is more like a suggestion. It would be really interesting to take the same approach that you introduced and maybe to consider it not for a single instance of the universe, but for a multiverse.
Oh yeah, possible, and that's that's how you introduce probability essentially. But you see, what we have when I throw a coin, we have two opportunities, and then we would have two different universes. In one, it would be heads, and another one would be tails. You know? But considering we have two different opportunities in the future, we have billions and billions and billions of opportunities in the past. Why? Because all different trajectories, all different initial conditions, they converge into equilibrium state. So, yeah, there are many possibilities, but probably if we want to be realistic about this world, we need to speak about multiverse of the past states of universe, in addition to multiverse of the.
I have a very brief question. This red line in the figure here, can it be viewed as an interface between the
Yeah,
states?
it is certainly. It's
an interface, right?
It's a barrier.
It's a potential barrier.
I understand that it's a potential barrier, but my question was different. Can it be viewed as an interface? And does it mean that the boundary conditions that you will have here at the interface, they might have a critical influence on the asymptotically long results that can be measured at asymptotically long times?
Yeah, absolutely. And
so boundary conditions at the interface are important.
The conditions, all these strange effects and sensitivities appear when this barrier is quite tall. So probability of moving from here to here, if it's large probability, it will just move. You won't observe any fine effects. But all these kind of fine effects appear when it can move. So it's not prohibitive, but probability of moving is quite small. That kind of interface is needed in this kind of experiment.
And boundary conditions are important to prescribe.
Oh yeah, of course. Boundary conditions. That's how resonance or non-resonance case. I've got a video about resonance and non-resonance case. Just solution of Schrödinger equation, but I don't have. Chair would kill me if I start showing.
I'm a peaceful person, but.
Okay, so I will survive it anyway. In every possible realization of the multiverse.
Okay. Yes?
Yeah, since you asked the question of like why the universe is like non-time reversible, from gas kinetic theory, we all know Boltzmann equation exists, and the key assumption is that if there's binary elastic collisions between particles, then you have Boltzmann collision integral. And formulating that equation, you get the H theorem, and that shows that you can always get entropy maximization, which is similar to the comment of a molecular diffusion. So what are you suggesting? Are you suggesting that in the presence of molecular collisions, there is a system that is going to keep the entropy constant, or are you talking about non-collisional system where the entropy is?
I understand the question. Let's move. First, when Boltzmann suggested this, he was grilled. he was grilled about this, and he finished up actually hanging himself. You know, this terrible,
I
terrible
know
story.
that, sure.
Sorry, and then no, but
I think the audience has been warned.
just no, it's Boltzmann, when he used, just think about this, he used reversible dynamics and he introduced irreversibility. Initially, he did not realize he made an implicit assumption, a very important implicit assumption, which discriminated directions of time. And this important assumption is causality. If you have two particles, their distributions are independent, because you know it's from Liouville equation you get Boltzmann equation, and then you need to have two particle distribution, and then you make assumption. And this assumption is that these particles are independent before collision, but not after collision. This discriminates the direction of time. This is causality. This is when you set initial condition, not final condition, exactly the same. That's what discriminates the direction of time. It's an assumption which is additionally brought into this. Causality? Yeah, of course. If you can physically set initial conditions and you have justification for them, yeah, of course, it works. It's a good principle. But in examples that I've shown you, initial conditions are very well, billion of years. They don't have direct influence. And causality should disappear then. And the causality that we assign to initial conditions. Or there is another mechanism.
So the question lies into the microscopic interactions of like systems.
Say it again?
The question lies in the microscopic interactions of the systems.
I don't know where the answer is. The question is, there is no explanation. There is a problem, and still after all this discussion, Boltzmann and others in Zurich and Zermelo, I think, you know, it was like a big fight between them, but there is still no explanation for at least some of the thought experiments we can run. And there must be one.
Okay, let's take this into the break. I think this is a great discussion, but